Like 8 hours of that.
I've never been involved. So,
Yeah.
I think you should go back.
This?
You send it backwards instead.
You want this to go back?
Yeah.
I always forget that.
Correcting me every time I said that we were doing Jupyter clues, and then he was like, well, yeah, Jupyter clues, yeah, but you don't have another notebook version of it, so I don't know what you want me to call it.
You got the best of that.
So 25%.
That's a big jump.
It's not until next Friday, so. It's kind of cool because it also shows points where you
Sorry, I'll let you.
so that was good. Because it was like,
I might have made that. What year was it?
Yeah, the camera is
We will be but this is the only option we have. Oh, actually, are you coming tomorrow to the U?
Oh yeah, I think I'm
Because I can't tomorrow. I'm working for something.
Oh, for this?
Yeah.
I think you wouldn't mind her transcribing.
Is that fine?
Yeah.
Thanks.
Make sure the sound's there. If you're not going to it.
Yes, it's there.
I guess while we're sort of waiting for the time to get started, you can keep talking, but if anybody's got questions about homework or anything so far, happy to answer them.
There's a really nice blog post by that Andre person, and I think he like made the assignments. Are we allowed to like use content?
Oh yeah. Yeah, so like at the bottom of every assignment it says, thanks to CS231 and for allowing us to use these materials. Yeah, this first homework assignment they have on that course, I think is awesome for like building up your intuition around like what's really going on. Because pretty soon we're going to switch over to using TensorFlow or Keras on top of TensorFlow or PyTorch or something like that. I mean, actually here it'll be TensorFlow, but you'll switch to something else, and you'll forget the fact that there's all this like complicated stuff happening beneath. And yeah, it's like gives you a good appreciation for all the hard work we're trying to do. Because it's kind of not fun to implement all these things. It's like, you know, it's like a lot of tedious work, but it's good. Yeah, but it's good. But yes, absolutely. I have no problem. I mean, the point is to learn, right?
But I'm actually thinking some of the code segments he posts are like, I think actually just looks nice. So I could see that as meaning.
If that's what it helps you learn, you know, do it. I don't really care. If you just are trying to get it done, too, I guess I don't really care. But hopefully you'll learn something along the way. Yeah. Good question. Yes, Andre Karpathy's feedback. He's now director of AI at Tesla, which may or may not have been a good move. We'll find out here in a little bit. Other questions? Okay, homework is due. Okay, anything else? All right, if not, I'm gonna get started. Always has to stay on. There it is. Okay. Okay, so real quick, where have we gotten to so far? So we talked about the general idea of score functions. So and we've just looked at linear score functions. We haven't built these up into multiple layers of stuff going on. So just score functions. So Wx here, there could be a plus b for the bias. As you'll see in the homework, and there's like a link to a page from the CS231N. Okay, to like a notes page where it shows it says something about a bias trick where if you just add a vector of ones to the column of ones to the end of this to W, then or I guess in this case it's a row. Then you basically get the bias gain just built into W, so you only have to have one term. And you actually use that in the homework, so anyways. Whether you have Wx or Wx plus b, you still have this linear term. And so anyways, we have these things called score functions. It's just a way of like putting our ideas down. We basically want to, in a classification problem, we want to score the class that is the correct class the highest. So then we have these different loss functions that we've talked about for determining like how close we are to actually looking like or getting the right answer that our largest score is actually for the correct class. So we discussed these two different ways of doing it. The top one there being the softmax, and the bottom one being the support vector machine or hinge loss. There's a good question from somebody I did the last time we did about this. So there's just like this is the loss, this is the contribution to the loss per data point per sample. And then what we typically do is we combine all those in an average to be the average loss over all of the data. So taking each one of these, whichever loss we've chosen, combining those, and then averaging them, so dividing by the number of data points. And then possibly adding a regularization term to express some desire for our weights to behave in a certain way. So we have this notion of loss function that gives us some indication of how well we're actually doing on this classification task with this particular set of weights W. And again, like zero loss means we're doing perfectly well, and any non-zero loss means that we're making some mistakes somewhere. We also talked about the fact that this average loss gives us some sort of crazy surface in high dimensions, and probably has lots of local minimum. And we're trying to actually find our way to one of those minima. And the way that we do that is through gradient descent. So we talked about this last time, where gradient descent looks a little bit like this. Does it come through very well? So we have weights right here at current iteration t. We compute the gradient of our average loss, and we choose some sort of learning rate or step size lambda, and we adjust our weights in the direction of the negative gradient. So that means the direction of steepest decrease in the loss, because we're trying to go to a minimum. If we're trying to go to a maximum for some reason, that would be a plus sign there instead of a minus sign. And that gives us a new set of weights, and we just keep doing that until this process hopefully converges, where we end up in some sort of minimum. So that picture there is just in 2 dimensions, what the loss might look like, and we're basically trying to get down to it. So one of the last things we talked about last time was the fact that we can have a lot of data, and it can be very computationally expensive to calculate, not necessarily calculate the gradient, but to evaluate it at all these points, all these data points that we have. We might have millions of data points. So, the average loss and therefore the average gradient, it might just take way too long to actually estimate. So instead, what we do is we actually estimate the loss by taking a small sample of all the data, which we call a batch or a mini batch, and we then calculate the average gradient on that. So this is like the actual average gradient, but instead what we do is we just say, okay, well, I really can't calculate this for a million examples, I'll just calculate this for, say, 120, 256, or some power of 2. It's always a power of 2. If you don't say power 2, it's clearly you don't know anything about deep learning. So you gotta say a power of 2. And yeah, then you just calculate for that. And so what happens is we know that this is like an estimate of the true average gradient, but that's okay because in practice it works just great. And actually it turns out, as we said last time, that this sort of promotes a more like a natural random walk within the loss surface that actually finds like better losses in some sense. It acts like a regularization in and of itself. Okay, great. So these are like all these important pieces here. So really, to try to train something, try to find the weights that give us the lowest losses. We're just trying to like calculate gradients and walk down the hill in these loss surfaces. So that's great. We just need gradients. So this is fine in simple cases like what's in the homework. You can actually like pretty easily work out what all the derivatives are and just sort of put it in there and just run your algorithm, and you'll find some minimum of your loss surface. And but it gets a little more complicated for more complicated types of, say, like scoring functions. But the thing that helps us like keep track of all these things and give us some sense of what is it that we're trying to calculate is we use some sort of like understanding of like the flow of data and parameters from input through to the loss function. That is called a computational graph. So these are not necessarily unique. You could have various operations could maybe be combined into one node in this or another. But the point is this just again to show some sort of flow from like input through to loss. And in a simple case, it maybe seems it's trivial to do this, but actually this becomes really important when we are actually doing real deep learning, because there's going to be so many nodes where like some sort of operation is happening that that becomes really critical to have these things. Plus, this is basically like all the major deep learning packages that you would use all basically construct a graph and use it to do what's called the forward pass, which is to put your data into the model, into the graph, and send it all the way through the losses, and then the backward pass, which is computing gradients all the way back through, which we're going to talk about today, a procedure called backpropagation. So in this simple case where we have our linear scoring function, and then here we have just one of the possible loss functions we could use, this hinge loss. It's pretty simple, right? We've got like computation is our input and our parameters, W, we multiply those things together as it's like a matrix vector multiplication. That gives us our scores. Those scores then go in some way to determine like that into our hinge loss. And then we might add, a regularization term. Maybe there would be one more node here for multiplying by the hyperparameter lambda, and that gives us our loss. But these things can get like pretty complicated. Here, in this case, something something is strange here. Like, it looks really low resolution here, and it also looks really low resolution here, which I don't understand. That's not clear with the connection. I don't know. Shoot. Well, it's not terrible yet, but if it gets terrible, I will play around with it. But yeah, so like in this case, it seems pretty reasonable to compute the gradients here. Well, I mean, it might take a little bit of work, take a little bit of thinking, but once you've done it, like you're done. But this can get really complicated, right? So even for like what now seems like a pretty naive implementation of a convolutional network, you might have tons and tons and tons of these nodes in this computational graph that are doing things like multiplications and additions and exponentiations and things like that. And you basically need to keep track of this flow of information from input to loss. And it can get even worse. Like here's the, it's hard to see, but here's a computation graph for something called a neural Turing machine. And why this is even crazy, because you see lots and lots of nodes within there that you have to do. But in something that's like sequential, to compute the gradients over sequences, you actually have to enroll the computational graph for every unit of time. And so not only do you have like this at every unit of time, but like the gradients from time step t affect time step t plus 1, and you unroll this thing, and like this graph becomes awful, and you don't want to do this by hand. This is why you go and get TensorFlow or something like that, and use that to do this, because that's hiding all this underneath a really nice Python API. But the point is computational graphs can get really tricky. And we need them. We need something to kind of keep track of. Again, the direction of flow from input to loss for our forward pass for computing loss, and then for computing gradients from the loss back all the way to the inputs. So these computational graphs are like essential in doing any sort of neural network training, especially when we're working with very deep models. So we're going to talk about back propagation now, which is the algorithm for, again, computing the gradients with respect to the parameters of our model, our weights. And this is like kind of like the final piece of understanding for like how all these pieces go together to optimize these things. So backpropagation is really, it sounds tricky, but it's really simple. If you remember the chain rule from calculus. So the chain rule is if I've got a function that has an input x, and it's a composition of functions, here's f composed with g, then if I want to compute the derivative of f with respect to x, the input, I just have to go through g. So the intuition here is the output of the function f changes with respect to x. It changes but the important part here is that it changes as g changes, and of course g changes as x changes. So, this is actually pretty simple to derive just using the definition of derivative, and it's nice that it just turns out to be a product. Like not anything more complicated than that. That you just need to multiply composed derivatives, but it's super powerful, and that's what we're going to spend time looking at today. So here's something somebody gave me once that's kind of like a fun way to look at this. The composition of functions is basically like stuff goes into G, whatever comes out of G goes into F. You see you got circles that get turned into, or spheres that get turned into cubes that get turned into some other nice shape, which I don't know what the name of that would be. But when you're composing it, basically it's like you just think of this all as one machine, and spheres in, funny shape out. But the important thing is like, again, just this product of derivatives to be able to get the total derivative over from the input to the final output. And I've shown this in one dimension. Of course, this applies in higher dimensions as well. You just sort of keep track of everything along the way. The important thing to point out here is our output. So I don't have it on here, but again, f composed with g, so f of g of x. This chain rule, as you take these derivatives with respect to the input, or each entry of the input, you have to go through basically all the intermediate pathways that are represented by y here. So the output of g on x. And so instead of having just like one term here, you have the sum over these terms. And this comes up all the time in backpropagation. It looks kind of scary, like the way it's written here, but even scarier written like that. But it's really pretty simple, especially when you think of it in terms of like the actual backpropagation algorithm. This is basically what we're doing. We're just going to be applying the chain rule over and over and over and over and over again. I don't know why I have that there. Okay, something very cool that exists and is part of this whole backpropagation thing is this notion of automatic differentiation. So there's all these identities for computing derivatives, right? Like if I have a linear function, w times x, and I take the derivative with respect to x, I just get w. Like that's just it's a linear function, and that's what derivatives are doing. Derivatives are giving you the best linear approximation to your function at any point of the function. And you remember like derivative of e to the x is e to the x again, and derivative of x squared is 2x, and things like that. Right? There's all these identities. So automatic differentiation is basically the algorithmic application of these identities to computational graphs. So the graphs tell you the flow, or they basically tell you all the compositions of everything from beginning to end. And then automatic differentiation just says, okay, I'm gonna use all those pathways and the identity derivatives to basically compute derivatives. So it's like a program that like basically keeps a database of all these identities, and just as it works through the graph, it just applies them as it sees those functions. And it's different from like symbolic differentiation, which is like basically what you learned in school, or if you ever used the program Maple for actually, like it gives you back like an actual, like the form of the analytic form of the function. It's different from that, and it's not numerical differentiation. We're not actually estimating the derivative by like, computing that quotient that like we looked at last week. It's actually just like looking up derivatives and applying them where they go. And this is like a very important part of training deep neural networks. Is again like basically all of your functions within your computational graph. Like basically they need to be differentiable, and they need to have a known identity. Otherwise, these things just don't work automatically. So underneath the hood, these derivatives are sort of being taken without you having to do any hard work. So, so I have this here. Yeah, these are the kinds of identities that we're talking about. Hopefully this feels like a review, or like a simple review. Okay, so let's actually start going through what we mean by backpropagation. So we're going to start with a really simple example. So we have this function, 3 inputs, x, y, and z, and the function itself is just x plus y, that quantity times z. So first of all, what we want is, we're going to take some, imagine we're taking some inputs here. So we need the computational graph for this. So in this case, this is pretty easy. X and y, they come together through an addition operation. And then then that sum comes together with z in a multiplication operation. So really simple computational graph. And then what I have here on the edges, up above on the edge, is the initial values of x, y, and z, as given here. So we've chosen some. And then what the result of that computation is with those inputs, right? So -2 plus 5 is 3. That's why the 3 appears after the addition node. And then 3 times minus 4 is 12, or minus 12, sorry. So great. So like the forward pass in a computational graph is usually super trivial. All right. So now we want to say the following. Let's compute the derivative of f with respect to our inputs x and y and z at the point x equals minus 2, y equals 5, z equals minus 4. So automatic differentiation would already have all this worked out, but we're not automatic differentiators, so we actually need to compute these derivatives ourselves. So there's a couple of different, at each of these nodes, the node can be represented by, something, some of the values here in the graph. So the first one, we give it the name of q. It's just x plus y. This is pretty simple. It depends on just x and y. Those derivatives are easy to do. Partial derivative of x with respect to, or q with respect to x is 1. Partial derivative of q with respect to y is also 1. And then the output f, instead of writing it as x plus y times z, remember it's the result of applying the multiplication to q and z. So that's what f is, q and z. So we can take the partial derivative of f with respect to q, and that's just z. These are just multiplied together. And also with respect to z, we get q. Okay, so we need all these to know all these things to then perform backpropagation. And it's called backpropagation because we're actually going to work from the end from the end of this computational graph, like what would represent the loss in our deep learning graphs, and we're gonna work from the end and move back towards the input. So the first one's always the easiest. We take the partial derivative of f with respect to f. What is that? 1. Yeah, that's the easiest one. But we're that easy only, right? Actually, we wouldn't be learning anything. That's not fun. So, so that's sort of silly to put down here, but it's just, I don't know, for completeness, that's what we have. So now, let's start thinking about this derivative right here. The partial derivative of f with respect to z, again, evaluated at these points, minus 2, 5, and minus 4. So what should happen here? What is the partial derivative with respect of f with respect to z? Well, it's q, right? So what number should go right here? 3. Yeah, it should be 3. It really should be 3 times 1 because we're really being careful about where all the partial derivatives are. We might have the partial of f with respect to f again. That's just one that's sort of silly. But yeah, it's just a 3. Again, because we know that our automatic differentiation tells us this, and we know what q is at these inputs. It's 3. Okay? Pretty easy. Now, the partial of f with respect to q. What should go there?
Z.
Z. What is z in this case?
Minus 4.
Minus 4. So minus 4 goes there. Pretty simple. And now, we have maybe our first interesting one. We're looking at the partial of f with respect to y. So why this is interesting is because we have to go through q. Right? We actually have to apply the chain rule here. And, oh, whoops, I was supposed to go so fast. Well, there's the answer. So the partial of f with respect to y is this, using the chain rule, is this product. Partial of f with respect to q, partial of q with respect to y. And we already know the partial of f with respect to q. We already computed that. That's minus 4. And the partial of q with respect to y, well, that's just something that we look up, automatic differentiation here. And that's just a 1. So we get a minus 4 times 1. And so our answer there is minus 4. And the comment here is when thinking about backpropagation, what's happening is, we're computing the gradients upstream here, at the end of the function, the output of the function, we're computing them and kind of working our way back. And when we work our way back, when we use the chain rule, we basically take all of our upstream gradients that apply in this case, and we multiply them with the local gradient in this case, q with respect to y. And this is just like a basic principle we're going to see over and over and over again. Okay, so not knowing what will happen when I hit the arrow here. When we compute partial of f with respect to x, what should it be? -4. Yeah, this is like too easy, right? Because, again, what will happen is this will be an x. Everything will be the same here, this will be an x. We know, again, what this is. We already computed that. That's -4. That's the upstream gradient. And then the partial of q with respect to x is just 1. So again, we get -4 times 1. And hopefully, hey, that's what we got. So, yeah, pretty easy. Like, here's like the caricature of what's happening in each one of these nodes of computation. We've got our local gradients. So x and y combine in f to give us z. So we look up locally in our automatic differentiation database what those derivatives ought to look like. And then we've got the gradient coming from upstream, loss with respect to z. And once it gets here to this node, we just combine it with the local gradient and send it on its way. So it's back because we're going from the loss backwards, and propagation is, doesn't you feel like it's propagating? So like it's moving along these train tracks, and it's pretty simple. It's just the chain rule, but remarkably, it's like the workhorse of everything that we're doing here. And for these simple examples, yeah, like boring, right? But for those far more complicated examples, this principle is just happening, just iterated over and over and over again, just as you move back through the graph. Okay, let's do a little more complicated example. Okay, so we have this function up here. It looks a little bit more like what we might expect from, from a neural network application. We have 1 over the denominator 1 plus e to the minus, and then you have this dot product with a vector w, length 1, 2 entries w1 and w, or w0 and w1, with the vector of inputs x0 and x1, and then some bias term w2. Anybody know what this function is called?
Logistic loss.
Yeah, so this is like logistic function sigmoid. It has one of these logistic-looking shapes to it, or like when the exponent is so when just like the exponent, the part in parentheses, when that is very positive, e to the minus that is nearly 0. So you're getting, on one hand, you're getting this is approaching 1, and when it goes the other way, when the part in parentheses becomes very negative, it then multiplies with that -1. That's becoming very large, and so it's actually approaching 0. So you get this nice smooth behavior in between. So this is giving you something like 1 and 0 and something like that. And so it's like approaching 1 as you increase the exponent, and it's approaching 0 as you decrease. And this is something that you'll see all the time in neural networks. Okay, so there's already some inputs there for both the weights and for the inputs, or some initial values for the weights and the inputs. And the forward pass has already occurred. All the multiplications and additions and then all these things. This is maybe it's worth stopping and looking at like how this computation graph is put together. You can again do this in a number of ways depending on how you, like what units of things you want to think of as a computation. But this is basically like every single possible operation is broken out here. So W0, X0, in our function over here, they're multiplied together. So that's like the innermost thing happening along with multiplying W1 and X1. And yeah, so those things are being multiplied together, both of those things, give me some output. Those things are added together, the W0 X0 plus W1 X1. And then the output of that is then being added with the bias term W2. So that's all coming here. And then once that output has been computed, then it starts to build up the rest of this. So it needs to multiply itself by -1 to get that negative in the exponent. So then that happens. And then it needs to be exponentiated. So that happens. Then it needs to be added to 1. This is also happening in the denominator. So that happens. And finally, we need to exist in the denominator. So we apply 1 over x to it to get it down. So there you go. That's like very explicit. All these different individual computations have to occur to get the output of this function. Okay, so let's start thinking about backpropagation here. So again, this first gradient is always 1, just to kind of get us started. It's the partial of f with respect to itself, so it's just 1. Okay, so let's do the next term, where we want to figure out what the gradient should be right here. So how do we do that? Yeah, so we need to know what the derivative of 1 over x is, which we have. We've just looked it up in our database, -1 divided by x squared. And the x that we are working with is the output, or basically the input to that function over x. So I don't expect you to know this off the top of your head how to do all those multiplications, but the point is that we take the value 1.37, we put that into our derivative, we then multiply that with the previous gradient from upstream, which is just 1 in this case, and we get a minus 0.53. Okay, so next step, this one's a little easier, we're just adding 1. So the derivative here is just 1. And so what's the gradient going to be here? What's going right here? We take the gradient of this operation. Yeah, we take the gradient of this operation. I'm evaluated at 0.37. So this is, the input plus 1. So here's our lookup right here. The derivative is just 1. So we have a 1 times the previous gradient, which is minus 0.53. So what is it supposed to go there? Yeah, minus 0.53. Pretty simple. Now we have this. Our operation here is exponentiation, so whatever our input is. So we have e to the x is our operation. We take the derivative of that. That's a simple one. It's just itself again, e to the x. We evaluate that at the input, -1. So that's going to be our local gradient multiplied with the upstream gradient. So we have e to the -1, whatever that is, times minus 0.53. So that gives us minus 0.2. Numbers chosen wisely. Okay. Next one, we're multiplying by -1. So again, the derivative of this is just whatever, the constant times the input is just whatever the constant is. So the constant's -1. So that's our local derivative.
X0.
X0.
Yep, X0. So the gradient here is X0. What's X0?
Minus 1.
Minus 1. That's our local gradient on the upper branch, multiplied by the upstream gradient. So what's going here? Minus 0.2. And how about the lower branch?
0.4.
0.4. Good. 0.39. What in the world? Rounding error. That should be a 0.4. I don't know why it's like that. But like you think like you've seen it all, like you looked over a couple times, and then it's only when you go through it carefully like this. That should be a 0.4. Okay, good. And then down here, what should the numbers be? Assuming we can do multiplication correctly.
Maybe 0.4, maybe 0.6.
So, yeah, it should be. Somehow these slides are roughing up the way that I thought they would. Okay, yes. It's actually showing up down here with this rounding error again. Okay, cool. So, not so trivial case, but still kind of trivial, but hey, now we know how to do this. This is what's happening when you're using TensorFlow, PyTorch, or whatever. This is what's happening under the hood. And it's not super complicated, but really, really useful. Okay, so a point being made here is that we broke out all the operations, one by one by one, like just like every single multiplication, every single addition, the exponentiation. But like I didn't have to do that, right? Like I can think of like all these operations right here as being that one operation up there, the sigmoid function, right? This thing right here, whatever the input is here in this case represented as x, I multiply by -1, then I exponentiate, then I add 1, then I take the reciprocal, 1 over that. So like that whole thing could have been a computational unit, right? We could just, instead of having like, 4 nodes, we could have had just 1 node, which is the sigmoid node. And we could have just like, again, in our automatic differentiation table, looked at the derivative of that and found that it is simply itself times 1 minus itself. So if we apply that same reasoning again, we look at this, we say, okay, the input of this is 0.2, or sorry, is 1, and so the derivative should be, let's see, why is this, that's not right, why is that a 1? Hold on a second. The input here, one second, I'm confused. Is the input to that gate is actually 1.
So why are we using 0.73?
Isn't that local gradient?
Say that again, sorry.
1 minus 0.73 times 0.0.73. That's not. Is that local gradient? You take derivatives.
Yeah, it is.
Times 1.
Oh, yeah, I'm at the wrong end of this thing. Right, like, yeah. The,
Let's go.
yeah, that is the output. And it's the output that we want, right? So I was taking, sorry. So this 0.73 is the output of sigma. So the derivative is 1 minus the output, not 1 minus the input. So, anyways, sorry. Yeah, so this whole unit right here, we want to compute the local gradient times the upstream gradient. So the local gradient is 1 minus sigma of x times sigma of x. So the sigma of x is this on this side, 0.73. 0.73 times 1 minus 0.73 is 0.2. And we can multiply by the upstream gradient, which is just 1. But the point in showing this is that we get basically the same, or we get exactly the same value here when running backpropagation when we actually use a coarser representation of the graph. So the point is these computational graphs are not necessarily unique, but they will always give you the same answer as long as you're doing all your derivatives correctly and keep track of the terms. Cool. Okay, so we already noticed this. You think of these as gates of information. When we have an addition gate or addition node, when we're running backpropagation, we already saw that this gets distributed to the 2 branches coming into that addition. We just pass the gradient, the upstream gradient to both. So that's nice. That's just an interesting thing to observe. So what happens when we have, say, the max operation, which occurs a ton in what we're doing, right? So we already saw in the hinge loss, there's a max. When we look at rectified linear unit activations, there's also a max there. So there's lots of taking derivatives of the function maximum of the 2 inputs. So what does a max gate look like here? What is it doing? So what happens is we're looking at the maximum of z and w. So let's think about that for a second. What is the partial derivative of the max of z and w, say, with respect to z? the answer here, just in general?
Indicate the function z greater than 1.
So it's
Okay, so I heard some things. So indicator function 1, 0.
Indicate the function 0 as
Yeah,
z
these-
greater than
Yeah, these are right. So it's either going to be a 1 or a 0. When's it going to be a 1?
when z is greater than w.
Good.
When z is greater than w.
When z is greater than w. When's it going to be a 0? Well, when 0 is less than w. What happens when 0 is equal to w? Well, this is where we just cross our fingers and hope it never happens. Yeah, it never will happen, but you can make your choice. Typically, a choice is made like this. To say like, okay, well, we'll just call it 0 when they're equal as well. You can make it's discontinuous. The derivative is discontinuous there, but you can make a choice. And honestly, it'll never happen. So, cool. So, what does that mean? Well, and also, obviously, this is symmetric, right? I could have put could have swapped the roles here and taken the partial with respect to w, and we just would have reversed the roles of w and z in this. So, so what is Max doing here? Well, Max is taking this upstream gradient, and this is already computed here. It looks to see which one of these is greater, right? Either z or w, and it gives to the greater one the upstream gradient, right? Because it's just multiplying it by 1. The other thing, we multiply by 0. So that's what we have there. We have the two. The upstream gradient is going up to the upper branch to z because it's greater than the w in this case. So you might call this a gradient router. So Max is somehow like routing the upstream gradient to the thing that has the higher value. Okay, that's kind of interesting to observe. What about with multiplication? What's happening?
Swap. Product is swap.
Good. Yeah, you have this swapping, right? The partial, what do we have there? X and y. So the partial, I can't see it over there. Partial derivative of x times y with respect to x is just y. And vice versa, the partial derivative of x times y with respect to y is x. So whatever's happening in the other branch, you use it to multiply the upstream gradient. So in that upper branch there, we took the upstream gradient and we multiplied it by the value at the other branch, and then vice versa. So yeah, so we might think of this as like sort of switching, swapping the values there, swapping the gradient. Cool. Yeah, gradients add at branches. If we have multiple ways out of a node, like if we're using that node to do multiple different things, like maybe we're doing one operation, going to some other part of the computation graph and doing another operation. When we come back to this node here, we're just taking the two upstream gradients and we're adding those together, and that's your total upstream gradient. Also, we can do this in a vectorized way, where everything we've been looking at has basically been single valued. We can do this in the multiple value case. So where like the inputs are vectors or the outputs are vectors. And everything applies, we just, instead of these gradients being scalars, they'll be vectors, they might be matrices, just kind of depending on what the different operations are. So, yeah, so like these might be matrices, and for some reason we don't call those gradients anymore. We call those Jacobians. Somebody named Jacob got their name. have the name on this for some reason. But yeah, it's just multivariate calculus, and everything still applies. So you actually do this in your homework where you if anybody's done it, you've already seen this, maybe you're already annoyed by it, but you basically at first you do a naive implementation of these things, which is just like you do 2 loops over, so like for like a matrix of weights, and you loop over all of the weights by row and by column. And so you're computing basically like the derivative at each entry of your weights, but you can totally do this in a vectorized way. In fact, in all implementations basically of this, that's always faster. So like you want to check yourself when you're doing your homework, when you're looking at vectorized operations, just think about what the input and outputs of these things are. So like for instance, the max function, which we just worked with, when you apply the max function, say, to a vector x, so like taking the max of that with 0, you think of both these things as being vectors, and you do this comparison element-wise. So if you put some dimension of something in, like in this case 4096 in, you expect to get something out as dimension 4096. Yeah, so in this case, when we're taking the derivative of this function f with respect to x, if our input is dimension 4096 and our output is dimension 4096, what does the dimension of that Jacobian matrix have to be? Somebody's saying it, I'm hearing a little bit of
4096 squared?
Yeah, 4096 by 4096. Basically, every single output of this, each of the 4096, you need to compute one partial derivative with respect to each of the inputs, right? So you actually have a matrix of dimensions 4096 by 4096. That's huge. Like this, like maybe it's nice to be able to do this vectorized, but wow, like if I'm not paying attention, I might have something that doesn't even fit in memory. Yeah, sort of something to remember here. Yeah, it has as additional aside here. So that's like for one. That's for one input. So now when you say use a mini batch size of, you can't use 100. That's bad. We need 128. That's a power of 2. Then yeah, like you multiply out. It's multiplied by 100 because that makes it easy to do multiplication. But now your matrix actually from the entire batch here is enormous. I mean, not even being able to be held in memory. So there's like very simple ways to optimize these kinds of things, but just something to be thinking about. Let's see. I'm not sure what the last question was there. Okay, so let's actually look. Let's do this together here real quick. We're going to compute. So this is a very simple matrix vector operation. This is computing the square of the L2 norm of the product W times X. So first of all, we need a computation graph. Yeah, okay, so we're taking X to be a vector of length n, and therefore W needs to be a matrix of size n plus n, or n times n. So here's our computation graph. We just multiply the two together, and then we pass it through the L2 norm, which looks something like that over there. When we're square, we're just looking at the square of each of the entries of the new vector, W times X. Okay, so let's think about this in vectorized form. We're going to go through this computation together. So we pick some initial values for W and for X. So n is going to be 2 here. And so we have W is that matrix, X is that vector. And we are again calling this node right here Q, the multiplication here Q. And that's what this looks like. The output here is this vector again of size n by 1, but in our case n equals 2, so 2 by 1. But just doing that's just matrix vector multiplication. And then finally our function is our output f of q is just to take that and do the norm squared, which is just basically the dot product of q with itself. Okay, so if we do that matrix vector multiplication, we get that q at that input is that, and then when we apply L2 norm to it squared, we get 0.116. So that's like a forward pass here from inputs to output. Okay, now we need to work our way backwards here. So the first one's always the easiest one. Upstream gradient, the first node is 1. Okay. Well, what do we do next here? Well, we need to compute the derivative of f with respect to q. So if you don't have like multivariate calculus like memorized, these things are always pretty easy to do if you just do them element-wise and then put all the elements together in the right size vector or matrix. It's the same thing, and it's much easier. So, for instance, when I'm going to be computing the gradient of this with respect to q, to do this first, this first backward propagation, I just look at my function f. I take one of the entries in any one of them qi, and I take the partial derivative of it with respect to qi, and these are really simple, right? So, there's a bunch of entries here that aren't qi, so those all go to 0 when I take the derivative. The one that it does have a qi squared, I take that derivative and I get 2 qi. So that's pretty nice. So that means that when I put all these things back together in a vector, it's a vector of these entries. And so I just get 2 times the vector q. So that's cool, that's easy. So again, if I'm doing back propagation, then I take my local gradient, which is this, 2q, times my upstream gradient, which is 1. So our q is up there, 0.22, 0.26. We're going to be multiplying that by 2, and times it by multiplying by 1, and there you go, you get that. 0.44, 0.52 as the gradient at that step. Now we need to go back through these 2 branches, this matrix multiplication. So this can seem pretty scary, but it's really not when you just sort of do what I was suggesting, which is you think about this in terms of each entry of W. So we want to take the derivative of this output Q with respect to this first case with respect to W, and we'll just do it with respect to one of the entries, ij. So ij is somewhere in here. If it was 1, 1, I would get an x1. If it was 2, 1, I'd get an x1. And that's what this funny thing is indicating right here. So I take one of these, oh yeah, one thing I failed to say is you pick one of these rows. So I'm picking one of the entries of Q, that's one of these rows here, and then taking a derivative of that with respect to one of the entries of W. So this funny thing here is the indicator function. Somebody already mentioned it, so clearly somebody is knows something about it. But what it is, it's 1 when k is equal to I, and it's 0 every other time. So it's like a really simple way to write down kind of a general form of this. So it's like, we call this the Dirac delta function the other day. It's 1 when k is equal to I, and 0 otherwise. So, so like, let's do this. Like for the first row, Q1, or k is equal to 1, so Q1. We take the derivative of that with respect to the entry W11. So I and j and k are all 1. Then this is equal to 1 when this is equal to 1 because k is equal to I, in this case 1 equals 1, so that's a 1, and we just get x1. And now let's change this. Let's go to the second row in this one. Q2, k is equal to 2. And again, let's do this with respect to y1, W11. So, so k is equal to 2. K is equal to 2. Y is equal to 1. So this is a 0. We would get x is equal to 1 in that case, but it's 0 times x1, so we get a 0 there. But if we did it with respect to 2, 1, we would get k is equal, k is 2, I is 2, so we get a 1 there. And then we're left with x1, which is exactly what we see here. So, I mean, really, multivariate calculus is all about like keeping track of indices, and not really much more than that. And think about automatic differentiation in this case. Like it's basically just keeping track of indices like this. So, so when we think about this, what this gradient looks like, this gradient is going to be a matrix, right? We're getting an entry for each one of the entries of W. So, yeah, so that's with respect to W. What do we have here? We have, yeah. So this is like putting the whole thing together in terms of the upstream gradient. So in this case, when we have the multivariate inputs and outputs, remember at the very beginning we said that if we want to do our back propagation, we're going to have to go through all the paths from F back to W. And so in this case, it's going through like each one of these entries of Q. So not just partial derivative of F with respect to Q, but through each entry of Q. So we have the term that we had before, the 2qx here, and we have the term that we just derived right here. And so our back propagation here, the term that we need to compute, in this case is this, 2qi times xj. So that's the Jacobian, that's the ij entry of the Jacobian that we're going to produce here. So that's what ends up there. So it's kind of hard to like compute it, to walk through each one of the entries on the board, but that's what we would get if you did this for each one. So like if we just, the examples that we did look at, so here let's look at the 1-1 entry, which is now up there. Let's look at the 1-1 entry. The 1-1 entry is going to take Q1, which is a 0.44, then it's going to take X1, which is a 0.2. So 0.44 times 0.2, and all that multiplied by 2 is a 0.088. So it's just keeping track of all the indices and putting them up there. And then similarly, when we want to compute the derivative with respect to y, we go through a similar exercise of computing the partial derivatives of q with respect to the other variable, in this case w, and you can verify that that is again the case. And hey, look, we get the same thing. And when you put these terms together, you can write down like the total derivative, not just the entry-wise derivative, but total as that q dot product with the transpose, giving yourself a matrix of entries. The point is, like, this gets really hairy, and thank goodness that there's like nice computer programs that do all this for you, because this would be really terrible to have to do on your own. Like no one would actually ever do any deep learning because it would just be terrible. But what's nice here is these things, like these relationships are usually pretty easy to derive, and they're pretty easy to check. Like for instance, it's really easy to check that you've got like the right dimensions at every step. If you don't have the right dimensions, you know right away that there's a problem. You can kind of try to fix that. Also, one second. Also, it's pretty easy to like check just again numerically that you're getting the correct gradient just in taking a very simple step in a direction and computing that gradient. Yes, go ahead.
We said 0.44 times 0.2 times 2, but it doesn't make sense. It's not 0.088.
What are you saying? Sorry. you're saying that that 2 times Q1 times X1 is not right. Is that what you're saying? Yeah, 0.44 times 0.2 is 0.08, but it doesn't have an additional 2 on there. Yeah, that's right. That whole thing should be multiplied by 2. Yeah, you're right.
It's not actually calculated and Q is 0.2.
Oh, it's 17. Yeah, it's
So now I'm really confused.
okay. When you say Q1, it's not 0.44, it's 0.22 because W times X is.
Yeah. You're saying that Q is 0.2.
Yeah.
Okay, good. Yeah. Right. Okay. So I'll try to restate this to make sure that we're all clear now. So there was a question that like the 0.088 was not right. Using like this formula right here. And I guess the mistake that was being made at first, and also by myself in checking it, was using this as the value of Q. But that's the upstream gradient. The value of Q is up above. So 0.22. So like we're looking at the 1 entry over here. Q1 is 0.22. X1 is 0.2, so those multiplied together would be 0.044, and then times 2 again would be 0.088, right? Okay. Yeah, okay. So, yeah, that was good the 20 direction. Hopefully those are correct. Those of you who are doing fast math in your head. Check those. Hopefully you're right on this. Okay, so yeah, so all of this is just to say like to give us like a really good appreciation for the software that we're going to be using to do all this stuff. And speaking of software, so you can think of this as being like your computational graph as being some sort of like list of all of these computations. And it's obviously not just like a totally ordered list because there's lots of branching and things like that could happen. But you know, just there you have some encoding of the way that information flows from the inputs to the outputs. And a forward pass here is basically just like going in that graphical order, that flow order, just continuing to apply that computational node, and finally at the very end of that to return whatever the loss is or whatever is that final output. And on the backward pass, going backwards through that graph and applying gradients and the rules of automatic differentiation going backwards. So like this is just some sort of pseudocode for what this might look like. What your graph might look like, and each gate or node in that graph has its own forward and backward operation, telling you how to go forward. In this case, in this very simple case of multiplication, you know, just taking your 2 inputs, multiplying together, and that's your output. But in the backward pass, to then apply the automatic differentiation rules and return your appropriate gradients. And this is like essentially what you're doing in your homework. It's not broken out to these like gate classes or anything like that, but this is essentially what you're doing in your homework. And this is exactly why we use these. It's really small. We use these frameworks, this software, because like all these different layers of like multiplication and addition and max, and then everything else more complicated than that, like convolutional layers, like we'll talk about next week, and I don't know, all the other things you want to do, are also things like the softmax operation, the sigmoid function, all that. They're already all built in to the software, and you just use the API and you just link them all together, and voila, you've got your computation graph and the ability to quickly go from input to output, and then add a gradient output back to input. So again, this is what you're doing in your homework. You're taking fairly simple computational graphs, like the softmax with a single linear scoring function, and you're computing all these, the scores, the margins, the losses, the any regularization term, and for like the forward pass, and then you're computing this for backward pass. Has anybody actually done this yet? Anyone in the next time you've done it? Super awesome students. Just kidding. Yeah. They are super awesome, but you're all super awesome. Yeah. So no one has? I saw maybe like a couple, okay. So, how did it go? Did it feel tedious?
I had to look a lot of stuff up. Like the gradients were difficult to like put into code.
Yeah.
I understood mathematically, but
Did you find it easy to do like in the naive multiple looping case?
that was easier.
And then hard to do in the vectorized case?
I still struggled like computing the gradients in the looping code. That took a lot.
Yeah.
The KN part, the first
Well, this doesn't apply to the KNN, the first part. This is to like the next couple parts, the softmax, the SVM, and the multiple layer neural network. Yeah, like it's not hard, but it's super tedious.
You gave us the softmax vectorized implementation. I saw that.
I gave it to you?
Yeah.
Oh.
Like it's in the template you have us copy.
Oh, that might be a mistake. I should go look that up. Well, Merry Christmas. That's funny. I tried really hard not to do some of it actually. So I better go get to the homework quick before it gets changed. Yeah, so it's like again, like these things aren't hard, but they're really tedious. And again, the intention here is just to make sure that you have some understanding of what's going on underneath the hood when we use these much more sophisticated software packages than the ones that we're writing here for the homework. Okay, so summary here at the end of the period. Yeah, so for very simple computations, no big deal. But for things that can be many, many, many layers of computation happening, we need some way to keep track of all these things. We use computational graphs to do that. Backpropagation, very, very, very simple idea. We're just recursively applying the chain rule, starting from the loss and working our way backwards, using all the rules of calculus to do that. Yeah, so the code that you'll write and that we're going to be using sort of as organizing this idea of like there's a forward pass and a backward pass. And yeah, forward is just a way of propagating the information from the inputs always to the output, keeping track of like the current input values, so that because we might need to use those when we compute the gradients in the backward pass. And that's really it. So I hope it doesn't seem so mysterious. Hopefully it feels really, really like conceptually simple, if not tedious. And the reason, and remember, like all this is just so that we can compute gradients, right? Like we have these complicated loss functions or complicated functions of the inputs and all the parameters in between. But in the end, all we're trying to do is compute a gradient. And the reason why we want that gradient is because we want to take a step in the right direction to minimizing our loss functions. Because a minimized loss function means that we're doing well on whatever task our loss function is designed to inform us on.
So are you back propagating like iteratively, like doing it multiple times, not just once?
Yes, right. So and again in the homework you'll go through multiple passes here, but the idea is that you start somewhere, usually some randomized state of the parameters, and then wherever you are, you calculate these losses, and the backpropagation tells you the gradient, and then using that gradient, you adjust your weights, right? So you just You're literally subtracting some scalar value of that gradient off of the weights. And there's far more complicated ways to do this, but this is like the most naive way, is just taking a step like that. And then you take those weights, those updated weights, and you calculate the forward pass, you get the loss, and then do a back propagation step with those weights. And you get a new gradient, and then you adjust the current weights with that, and now you get the most updated weights, and you just keep doing that until you get some sort of like converging behavior, which you're finding the bottom of some well in that loss landscape. Yep, exactly. Yeah, so it's an iterative process, so it can be quite slow. And we wouldn't even be having this class today again if it wasn't for GPUs that accelerate these kinds of operations, these matrix multiplication operations, many, many, many times. Otherwise, we'd just be back in the 1980s and have like 10 weights and things were doing really well. I mean, literally, like the biggest networks have millions, maybe hundreds of millions of parameters. It's crazy, right? This is not your grandparents' network for sure. I don't know if my parents were doing that. My word. All right. I'm happy to take any other questions, but we're done for today, so thanks. Yeah, so I should yeah. So if I comment 2 months ago, other systems, you might